Hello and welcome back to solving trig equations algebraically. And this is our final look at it with a real humdinger of an example. So here's my example. You can see it written out. Looks like a kind of a quadratic looking equation. And so the first thing I'm thinking I'm going to do is I'm going to replace all of these cos 3x's with q, just to make it a little bit easier to look at. Just because then I look at it and I see, yes, it's 2 times cos 3x squared, or q squared, plus 5 times cos 3x, which would be 5q, minus 3 equals 0. And I go, hey, I think that this thing factors. So I'm going to go ahead and factor it. So I think we're going to have a 2q times another q. Okay, and now I need two numbers that multiply together that make negative 3 in such a way that I can build a positive 5. So I'm thinking, what if I put positive 3 here? So I'd build up a 6q, and then I'd go minus 1q. So I think that's it, all nicely factored. So now I'm going to replace the q with cos 3x. So here's what we have. We have this guy, which we want to turn into 0, and we have this guy, which we want to turn into 0. Okay? All right. First things first, the one on the right here is actually the easier one to solve, because look at this. Cosine of 3x, and we're trying to make that equal to negative 3. Well, guess what? If you think of the graph of cosine, okay, and I'm just going to draw a little version of it here. If you think about its maximum, it's 1, and its minimum is negative 1. Now, even though there's a 3 in front of the x here, all that does is kind of compress the graph. But it's not going to change the fact that our maximum is 1 and our minimum is negative 1. Does this thing ever equal negative 3? The answer is no. So this has no solutions on this side. This doesn't solve. No such x will work. So it's all down to this guy here. So let's isolate the cos 3x. We'll bring the 1 over and then divide out by 2. Okay, so yeah, this will work. Cosine does equal 1/2. Now, I'm going to need some more room here. So I'm just going to clear the screen and then get to work here. But what I'm going to do is I'm going to write the original here, what we're trying to solve. And then I see this change with the period. So I'm going to ignore that and just say, well, let's look at cosine. When does it equal 1/2? Now, I'm thinking in a special triangle, this is actually going to work. Boy, that's a curvy looking triangle. But anyway, 2, 1, and a root 3. Well, I'm thinking the cosine of this angle here, of pi by 3, that's going to work perfectly. I'm getting 1/2. So I'm going to list my my answers here. Oh, I better look in the other quadrant too. So where is cosine positive 1/2? It would be positive 1/2 there, and a positive 1/2 there. My one angle here that I've just determined is pi by 3. That's one of my answers. And then we're going to build the same reference angle down here. So there's a pi by 3 there. So let's name them. So it's pi by 3. And then the one down here, this is like saying 2 pi minus 1/3. Now 2 pi is like 6/3, right? Because you got your 2 pi, which is like 6/3 pi. And then I want to take away 1/3, right? I want to swing to 2 pi and then back it up 1/3. So I think it's going to be 5/3 pi. And remember, that is plus multiples of the period. And the period for cosine is 2 pi. Now, this is all great, except for one thing. We're dealing with 3x. If we want to solve for x, we have to contend with that 3. But that's pretty easy to do. You just take your kind of solution package, and then you times each of these by the reciprocal of that 3, or 1/3. Now, I'm going to clear out a little space here, so I'm going to get rid of that. Put my solutions, my solution generator in here. So here's what my general solution looks like. It is pi by 9, right? Because I'm multiplying 1/3 times pi over 3 plus, and then 1/3 times n times 2 pi. So it kind of looks like this. Okay, so there we have that. And then the one on the bottom here is going to be 5/9 pi. Okay, so what this is, our general solution is going to generate solutions for us. Because remember, in the original question, we were supposed to list all the solutions that fall between 0 and 2 pi. So we're going to have a set of answers here. Okay? So what I'm going to use is I'm going to use this stuff here as my generator and figure out how many solutions I can get here. So when n is 0, it wipes out this. I have pi over 9. So that's one of my solutions. Okay, pi over 9. Now, what about when n is 1 and I add 2/3 pi to this pi over 9? Well, let me show you. Sometimes it's a little bit easier. Yeah, because I got a limited space here, I'm just going to delete the 2/3. And you'll see why in a second here. I know you're probably thinking, what is he doing? But I'm going to show you why. If we take 2/3 and we write it so it is over 9. Now 2/3 is the same as 6/9. Okay? It actually makes it a little bit easier here because now I go, okay, what is pi over 9 plus 6/9 pi? Well, that would be 7/9 pi. Okay? And that's still within 0 to 2 pi. I can still throw another one at it. I'm going to throw another 6/9 at it. So basically, I'm adding another 6 to my numerator. Now, is this within 2 pi? Yes, because 2 pi, remember, 2 pi, the end of the road is in the world of ninths. It would be saying we can't go beyond 18/9. So 13/9 is very acceptable. But if I added another one of these, okay, another 6/9 to that, well, goodness, then we're going to be at 19/9, and I would have gone over 2 pi. So that's the end of the road. That's how many solutions I got out of this first generator. Now I got to list all the solutions that get cranked out of this one. So there is a 5/9 pi, and that's when n is 0. Then when n is 1, I'm going to add a 6/9 to that. So that would be 11/9 pi. And then I could add one more of these 6/9. So I'd have 17/9 pi. But that's the end of the road. Because if I go and add another one, then I go beyond 2 pi. So this is my set of solutions that falls between 0 and 2 pi. These are my specific solutions. And of course, these are the general solutions that we used. All right, well, that's a pretty busy example, but that's the end of it. And that's where I'm going to stop. So we'll catch you later.